Hello everyone, this is Professor Iris Miano giving you your very last lecture video concerning sections 11.4 on mathematical induction and 11.5 on the binomial theorem. So while you will not have a semester exam on this material, these topics will be included in your final exam. So I'll definitely go into more detail in class on what you're expected to know in regard to these last two sections. Okay, so let's go ahead and get started. The principle of mathematical induction is an incredibly famous methodology associated with writing proofs. And it has everything to do with being able to start the process associated with an equation or a relationship, and assuming that the next step in the process will be made, and then being able to show that the next step after that will also be valid. So a lot of folks liken this to a domino effect. So enter figure 10 here, where you see a series of dominoes lined up. And the idea is you need to push over the first domino. That is showing that the n equals 1 case is true. So show n equals 1 true. That's akin to pushing over the first domino. And then you will, after that, according to, here's the formal write-up of like what the principle of mathematical induction is. Go ahead and read it, of course, but I want to just kind of a little bit less formally talk about the process. So step 1 will be show n equals 1 is true in the process. Step 2 will be assume that n equals k is true. I know, so it's a little bit silly maybe to think about, oh, we just have to replace n's with k's in the relationship that's given. Yes, that's exactly it. And so we're just going to replace n's with k's and assume that that relationship is true. And then step 3 is going to be show that the n equals k plus 1 is true. And you're going to use what was assumed to be true in step 2 in order to show that step 3 is copacetic. Okay, so I really don't have much more to say about the process other than outlining these 3 steps. And so I'm just going to show you several examples in which we use the principle of mathematical induction to prove that a given statement is true for all natural numbers n. And here is the process. Let's go ahead and start with number 2, in which we are given a sum in which the first 3 terms are explicitly shown. That's 1, 5, and 9, and of course they're being added. And then the nth term has the form 4n minus 3. So that is supposed to all be summing to n times the quantity 2n minus 1. So what we want to do is use this 3-step process shown here in blue, right, in order to prove that this is true for all natural numbers n. Any n you can think of, okay? So any n that's a natural number, that is, okay? So that's your 1, 2, 3, 4 off into, pretty much positive infinity. Great. But it has to be a natural number, so no fractions or decimals or anything silly like that. Great. So let's go ahead and go through the process. So again, step 1 is show that it's true for n minus 1. Or sorry, n equals 1 is true. My bad. N equals 1 is true. Okay, so then for this one, you can either just take the first term, or it's a little bit more, what's the word I'm looking for, of a thorough process to actually take the structure of that nth term and plug in a 1 for n. So that'll be 4 times 1 minus 3 is, or minus 3, sorry, I put an equal sign. Let me erase that right there. Minus 3. Is that equal to, we'll take the right-hand side of the equation and put in a 1 for n there. Okay, so we'll simplify it. We got 4 minus 3 on the left-hand side. We got 1 times 2 times 1 is 2 minus 1 is 1. So it's 1 on either side. Cool. 1 equals 1, yes. So that is complete on step 1. We showed that n equals 1 is true. We plugged in a 1 for n on both sides of this equation, just using that last nth term as structure for what n equals 1 term would look like on the left-hand side. The right hand, or excuse me, and then the right-hand side is shown in its entirety, and we're just plugging in a 1 for n there, and it worked out. Okay, so now step 2 is where you're going to assume n equals k is true. So what does that look like? Specifically, we're going to assume and then write what the relationship looks like, replacing all n's with k's. So 1 plus 5 plus 9 plus ... plus the quantity 4k minus 3 is equal to k times 2k minus 1. And there's nothing to do here as far as simplification is concerned. You are simply stating that we are assuming that this equation is true, that no matter what we would put in for k, it's going to be true. Now, we need to show, oh boy, I've already run out of room here. Hold on. Let me give myself some extra room here. Just a moment, bear with me, folks. And we want to give ourselves a whole nother page, like it's just going to be way more than you need. But yeah. Okay, so we're just going to assume that that's in play there. So now let's put step 3, and we're going to start it on the next page just to give ourselves plenty of room. Step 3 is going to be, we want to show that it's true for the n equals k plus 1. So this is where algebraically there's a little bit of trickery afoot, and I want to show you what the trick is, basically. Okay, so what you'll want to do is go ahead and write down the relationship for n being replaced with k plus 1s instead of k's like we did in the previous step, okay? So what does that look like? So we're going to say we have 1 plus 5 plus 9 plus ... and go ahead and put that kth term in there. So by that I mean 4k minus 3, right? And then go ahead and add to that the k plus first term, which is, and I'll go ahead and put a couple of different grouping symbols here, 4 times k plus 1 minus 3, like so. Okay, and that's supposed to be equal to not just k, but k plus 1 times 2 times k plus 1 minus 1. So this is what we're trying to show. So we're essentially showing this is true. And so here's where the algebraic trickery comes into play. So what you'll want to do is take the n equals k case that we're assuming is true and add the k plus first term to both sides, which specifically for this relationship is 4 times the k plus 1 minus 3 to both sides. Okay, so again, take your n equals k case, that's the 1 plus 5 plus 9 plus ... plus 4k minus 3 plus this bit, right? So it's looking a lot like what we're trying to show. Okay, don't worry though. We're going to take, right, this is just me adding it to the left-hand side, this k plus first term according to the sum, and that's going to be equal to k times 2k minus 1, but then add this to it, right? So this was the kth case, n equals k case on the right-hand side, but then add to it the thing that we were adding to both sides to that n equals k case. So that'll be 4 times k plus 1 minus 3. So now what we want to do is take what we have over here and we want to get it to match what's going on right here. Okay? So we've got to get this to match. So get it to match. So we're not going to touch the left-hand side of the equation anymore. We're just going to leave it be. We're going to manipulate this right-hand side. Okay, so what do I suggest that you do in order to make this look like the k plus first right-hand side of the equation? Well, I recommend that you distribute and combine like terms, and then you're going to get a quadratic in k. So watch this. Okay, so I'm going to give myself another, color here in order to show the distribution here and here, here and here, and then I will also subsequently combine like terms. Cool, so this will become 2k squared minus k plus, and we could drop the brackets at this point, and when we distribute through here on this 4, we can drop the parentheses, and that'll give us 4k plus 4 minus 3. So go ahead and combine all like terms, and you'll get 2k squared plus 3k plus 1. So go ahead and factor this. Diamond method, whatever your go-to method is, okay? And you're going to find that this factors to k plus 1 times 2k plus 1. Right, just checking my notes there. So factor this. If you'd like to see me go through the process of factoring this training wheel, I'd be happy to do it. I'm just, in the interest of time, going to go ahead and skip that step and say this is the factored form of it, and then recognize that we are painfully close to what we want up here in what's underlined in green, okay? We want this to be k plus 1, okay, so we have the k plus 1 terms right here, but here in this bracket we have 2 times the quantity k plus 1 minus 1. Now check this out. If you were to distribute this through, right, and combine like terms, you would get this 2k plus 1 quantity that we have right here. So it's just a matter of being able to recognize that this is actually already equivalent to this, and we can go ahead and just say they're equal to each other. So hold on, let me just go ahead and prove it to you over here in green with a little bit of a sidebar, in which we say, all right, 2 times k plus 1 minus 1. If I was to distribute that through, I'd get 2k plus 2 minus 1, and that equals 2k plus 1. Yep. So you can go ahead and like work backwards on this and just go ahead and say that this is 2k plus 1 times bracket 2k plus 1 minus 1. Now, how would you know to do that? Well, really, it's just a matter of being able to see these kinds of examples enough times, and then you'll pick up some of these tricks. So yeah, so we were able to demonstrate via algebraic manipulation on the right-hand side of this equation for the k plus first, for the k term, excuse me, the kth term, in which we added the k plus first term in the sum to both sides, we were able to make it match up with the right-hand side of the k plus first term that we were trying to show. So getting this to look like this is the proof conclusion right there. Okay, so therefore we would be able to conclude that the original relationship is true for all n values. Okay, again, let me just reiterate the process. We showed it was true for n equals 1. We assumed it was true for n equals k. And using that assumption, we were able to show that it was true for n equals k plus 1. And if it's true for the next value after any natural number k, then that means it's going to be true for the next value after that, and the next value after that, and the next value after that. Just literally a domino effect is in play. Okay, great. Let's practice this again for this relationship here. So now we have some exponential stuff going on here, but it's the same exact process. Okay, so I'll go ahead and start it off in green, and then we'll do accent colors in this sky blue business. All right, so show, this is step 1, show that it works for n equals 1. So go ahead and take the structure of that last term and say, all right, is 3 to the 1 minus 1 power equal to 1/2 times 3 to the first power minus 1. Okay, well, 1 minus 1 in the exponent, area is 3 to the 0 power, right? And so 3 to the 0 power is going to give you a 1. And then if we take 1/2 of, what's 3 to the first power minus 1? Well, 3 to the first power is 3, minus 1 is 2. Right? So no matter how you slice it, you get 1 on both sides of the equation. Cool. So we just showed that it works for n equals 1. Cool. Number 2. Now we get to assume that it works for n equals k. This is the easy part. Just go ahead and rewrite the relationship given to you, but with k's instead of n's. It's literally that simple, step 2. Okay, so we get to assume that we have 1 plus 3 squared plus dot 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 plus 3 to the k minus 1 is equal to 1/2 times the quantity 3 to the k minus 1. That was easy, right? All right, now herein lies the hard part. It's easy to start writing step 3, but to get the k plus first right-hand side to match, the the kth right side with the k plus first term in the sum added to it, is where the algebraic fun really comes into play. Okay, so let me just go ahead and write down the process here. Now we get to show it works for n equals k plus 1. So the first thing that I like to do is is to write down what the k plus first step in the relationship looks like. So we've got to show that 1 plus 3 squared plus dot 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 plus 3 to the k minus 1, minus 1. So that's the kth term, right? But then we add to it the k plus first term, which is just going to be k, because k minus 1 plus 1 is just a k. The minus 1, the plus 1 cancel out. It's going to be equal to 1/2 times 3 to the k plus first power minus 1. Okay, so the process goes like this. So this is still just putting specifically what you're trying to show, okay? You're trying to show n equals k plus 1 works, which means you're trying to show that these two are equal. All right, so the process is still the same as the other example. So we're going to take the n equals k case and add specifically 3 to the k to both sides and make it match up with what we see right here. Okay, cool. So again, take your n equals k case, which in this particular problem is 1 plus 3 squared plus dot 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 plus 3 to the k minus 1 power plus 3 to the k, and set that equal to the original n equals k right hand side of 1/2 times 3 to the k power minus 1, and then add 3 to the k right to that side. Okay, so this is just, again, to be abundantly clear, in orange what I'm going to do is underline the n equals k case and show that I added 3 to the k to the both sides. Okay, now I'm just going to, from now on, manipulate the right-hand side of this equation, and I want to make it look like what I'm going to box up in this magenta E purple, or I'm going to underline it rather. Magenta E purple, sure. So this is going to have to match with this, but it doesn't match up at the moment, so I need to put on my algebra hat in order to make them the same, okay? Now, it's true that, like, I'm kind of, you know, already know that they're going to be the same, but I have to show it, right? I have to make them the same. That's the whole process associated with this proof. So what do we need to do in order to make this happen? Basically, we're going to distribute this 1/2 right here and here, and then combine like terms. So watch this. We'll have 1/2 3 to the k power minus 1/2 plus 3 to the k. Okay, so we have half of a 3 to the k and a whole 3 to the k, or 2 halves, right? 3 to the k power, if you wanted to. If you wanted to add this one to this one, you would have a half 3 to the k power, and you have a whole 3 to the k power. Well, that means you have 1/2 3 to the k powers, or 3 halves times 3 to the k power in combining these like terms, and you're going to still subtract 1/2 from that. All right, at this point, you may notice that you have a common factor of 1/2 that you could pull out to the front, which I would really like to do, because the form that I'm trying to get this right-hand side in has a common factor of 1/2. So I'm going to go ahead and pull it back out once again and take a look at what's left. We will have, therefore, a 3 times 3 to the k minus 1. Cool. Now check this out. This 3 factor that's being multiplied by the 3 to the k, it has an exponent of 1. Whenever you multiply exponential expressions with the same base, what do you get to do to their exponents? You get to add them. So 1 plus k is going to be equivalently called, you know, k plus 1. And then I will have my right-hand side exactly how I want it. Because watch this. Doesn't this look familiar? Here, I'm going to underline it in this purple to show you that they exactly match up here. Right? Look at that. 1/2 to the quantity times the quantity, 3 to the k plus 1 power minus 1. Down here, 1/2 times the quantity, 3 to the k plus 1 power minus 1. They match. Okay, so again, let me reiterate the process because it's kind of a lot. We first, for any relationship that we are being presented with that we want to use the principle of mathematical induction to prove, we want to show that the relationship is held for n equals 1. then you assume that the relationship holds for n equals k. So just go ahead and write down that same relationship that you were given, replacing all the n's for k's. We're going to use that. Then you want to show that this relationship holds for n equals k plus 1, the next, iteration after that. So you will essentially show, and it helps, I think, to write down what the k plus 1 case looks like, okay? And then you're going to use the n equals k case. We're going to copy that down and add that k plus 1 term in the sum to both sides of the equation, again, from the n equals k case. So take that case, add for this particular problem, it'll be 3 to the k on both sides, and then make the right-hand side look exactly like the right-hand side for, this right here. Then make this right-hand side, where I'm hovering with my cursor, look exactly like the right-hand side for the explicitly written k plus first case. And we did some algebraic manipulation, and we got them to match, as you can see in both things that are underlined in purple. Okay, so like I said, you're going to need to put your algebra hat on. And so the purpose of these examples that I'm demonstrating for you is to show you some common tricks that you can use. Basically, it's like you evaluate as much of the probably obvious things that you could do to simplify the right-hand side, and then you just want to look back at the k plus first right-hand side and just try and do whatever you can to make those two match up. Okay, great. So let's do this one more time with the number 20, but it's going to have a little bit of a different setup because it's not an equation, really. We just want to show that this particular expression, n to the third power plus 2n, is divisible by 3. So it's, it's a little bit of a different initial thing that you're given, but the process is still exactly the same. You still want to, step 1, show n equals 1 is legit. Is it legit? Oh, I don't want to put a question mark there. I want to show it. I'm pretty confident that it's gonna be having a divisibility by 3. Let's show it explicitly though. So 1 to the third power plus 2 times 1 equals what? Well, that's 1 plus 2, which equals 3. Yep, this is divisible by 3. 3 is divisible by itself, so check on that. Cool, done. It's legit. Step 2, assume that k to the third power plus 2k is divisible by 3. I don't know what k is, don't need to know. I get to assume that if I take k, cube it, and then add its double, that it's going to be divisible by 3. Cool, moving on. Literally, step 2 is the easiest one to do because you're just replacing the n's with k's and calling it good. And you're going to use that to show now that k plus 1 quantity cubed plus 2 times the quantity k plus 1 is divisible by 3. So in order to show this, we're going to want to expand this expression right here, okay? So what does this look like? Well, k plus 1, that quantity cubed, plus 2 times k plus 1, looks like this. Now this one, we're actually going to get into how, like what the pattern is associated with expanding it in the binomial theorem, so it's like stay tuned for that. But I'll just tell you, k plus 1 to the third power is k to the third power plus 3k squared plus 3k plus 1. And then taking 2 and distributing it over k plus 1 yields plus 2k plus 2. Okay, so rearrange these terms right here in a very, very particular way, okay? Notice that in the assumption that we got to make in step 2, we had k to the third power plus 2k. Do we have a k to the k to the third power in a 2k term? Sure enough, we do. So go ahead and put those two next to each other. And you can do this because addition is commutative. We can reorder these terms however we see fit because they're all being added together, right? So this is equal to k to the third plus 2k plus 3k squared plus 3k plus, and let's go ahead and also combine like terms right here, plus 3. Okay. Now, this is where it gets to be fun and interesting in my opinion. Okay, so we get to group these things however we want to because, again, all of the terms are being added and addition is associative. So I'm going to go ahead and choose to group these first two together and then group these last three together, in which to say, look at this, k to the third power plus 2k in my assumption here is divisible by 3. So I know that this is divisible by 3. Oops. Based on my assumption. Because of step 2, assumption. And then check this out. Do I get to assume that this expression here is divisible by 3? Well, yes, it does, because I explicitly have shown here that each of these terms has a factor of 3 in it. So, like, clearly, by any casual observer, we can conclude that this expression right here is divisible by 3. Since all terms have a visible factor of 3. So, therefore, so you guys ever seen this triple dot in a triangle configuration? It's mathematical shorthand for the phrase therefore. We get to say that k plus 1 to the third power plus 2 times k plus 1. The whole thing is divisible by 3. If all of the terms taken in specific groupings are divisible by 3, then the entire expression is divisible by 3. Okay, great, cool. Let's do one more, and it's going to be a lot more general, I guess, than some of these other ones because we're going to have lots of unknowns going on, but we're still going to be able to use mathematical induction to prove that the following relationship is true for all n that are natural numbers, for all natural numbers n. Okay? So notice that we have the sum here, and we are given that last term, and that's going to give us the structure to be able to use to be able to show that the first n equals 1, case is in play. So that's going to give us our step 1. One thing that we want to note here is that, and I want to switch up the colors just for funsies. Let's go this dark purple. And so notice that we're given a stipulation that r cannot equal 1. Okay, noted. Because what would happen if r equaled 1 on the right-hand side of the equation? Well, we would have a denominator that's a 0. So obviously we can't have that. We're not going to mess around with that. So that's why we have this stipulation here. Cool. So let's go ahead and use mathematical induction. Step 1. Show it works for r n equals 1. Show this works for n equals 1. So again, use the structure of the last term in the sum to illustrate this. That means you'll have a(r) to the 1 minus 1 power is equal to a times 1 minus r to the first over 1 minus r. Okay, now 1 minus 1 is going to be a times r to the 0th power, and then this is going to be a times 1 minus r over 1 minus r. So we get to say that a couple of these things are oneing out, which is what I like to say, right? So this factor is oneing out by virtue of being raised to the 0th power. This factor is oneing out by virtue of it being a fraction of having values of itself, it over itself. I'm not sure if that made sense. The numerator and denominator of this fraction are equal, and therefore the value of this fraction is 1. Cool. Probably didn't even need to say that out loud. Great. So this is a equals a. Cool. That is true, no matter what a's value is. So it looks like this relationship works for n equals 1. Step 1 achieved. Step 2, the easiest step in the world. Go ahead and write down this relationship, replacing all of your n's with k's, and assume that it's true. Assume that a plus ar plus ar squared plus ... plus ar to the k minus 1 power equals a times 1 minus r to the k over 1 minus r. Great. So we get to assume that this is true. All right. Now let's show, this is step 3, show that a plus ar plus ar squared plus ... plus ar to the k minus 1 power plus ar to the k, because that'll be the k plus first term, right? Because k minus 1 plus 1 is just a k. The minus 1 and the plus 1 cancel each other out, is equal to, okay, and then put this right-hand side of the equation. It's going to be 1 minus r to the k plus first over 1 minus r. Okay, that's a little sloppy. Let me rewrite this exponent. Sorry. There we go. K plus 1. That's a little bit better, only slightly. Okay, great. So again, we want to take the n equals k case that we had in step 2, and we're going to add a r to the kth power on both sides of it. All right, so, and I'll put in my notes what I'm doing here. Take n equals k and add a r to the k to both sides. And then you got to make it match this over here. So that's where the challenge really lies. Okay, let's set this up. We've got a plus ar plus ar squared plus ... ar to the k minus 1. Okay, so this is the left-hand side of the n equals k case. So we're going to add ar to the k power, and that was the n equals k case was equal to a times the ratio 1 minus r to the k over 1 minus r, and then we're going to add to that ar to the kth power. So now I'm going to have to try and get this, what I'm hovering over with my cursor, to match this up here. And if I can do that, I have written my proof. So what are we going to do in order to make this happen? So this one's far more challenging than the other ones that we've covered so far. So here's my little bit of trickery. See how we're dealing with a ratio, and we want to add these two things together? Basically, we want to deal with this the way that we would fractions that we want to add together. We want to do an LCD type thing. So let me choose, let's choose this orange color to iterate what the LCD is. The LCD is 1 minus r. 1 minus r. So what I'm going to do is I'm going to build up this term right here to have a common denominator with this first term so that I can add those numerators together. Here we go. So this will be a times 1 minus r to the kth power. So that's basically this a jumping up with the numerator here, but I'm going to wait to distribute into a second step. And then here I will have plus a r to the kth power times 1 minus r. And that's all over a 1 minus r. Okay, so if you want to see a little bit more algebra associated with that, I can certainly do that in class. But in the interest of time here, I'm going to go ahead and just move forward. Now I'm going to go ahead and distribute my a's here and my a r to the k's there, and then watch what happens. We have a minus a r to the k plus a r to the k minus a r to the k plus 1, right? Because it'll be a r to the k times r, the r being to the first power, so I can add those exponents together. Check out what's happening with these two middle terms. They cancel each other out. Fun, right? Oh my god. Oh, sorry, I forgot to mention that this is still all over 1 minus r. And now I'm left with a minus a r to the k plus 1 all over 1 minus r. We are so close to getting this to match up. All we need to do now is pull out this common factor of a, bring it to the front of the ratio, and we will be left with 1 minus r to the k plus first power all over 1 minus r. Great. And so if I just scroll up the slightest little bit, oh, sorry. So I won't be able to have it all on one page because my handwriting is so incredibly large here. I'm going to actually take a different color. We'll do this light blue. And we'll say that this, in fact, does match this down here. So I'll be able to, yep, and circle them up. They match. They match. So fun. All right. And that's a wrap on mathematical induction for now. Of course, if you want to see some more examples of this in class, I'd be happy to demonstrate. Let's go ahead and switch gears. Might feel a little jarring, switching gears to the binomial theorem. Now, the binomial theorem is called the binomial theorem because it is a mechanism by which you can expand a binomial raised to any natural number power. So, 1, 2, 3, 4, 5, 6, right? And on and on and on. The power, that is, okay? There is a component that you will need in order to make this expansion possible, and it's going to be called the binomial coefficient. That's what this n over j business is formally called. Okay, so what else do I want to say about that? So, we're going to have to review what we know about factorials, they being defined as, well, n factorial is n times n minus 1 times n minus 2 times n minus 3, on and on and on until you get all the way down to a 1, right? That's when you know you are done with that product. And so if you want to find the value of this particular binomial coefficient, you will use this formula right here. Again, remembering what your factorial definition is. Okay, there are some particular binomial coefficients that you're going to want to take into account. Like, for instance, would you start off this process, and these will become more apparent, like where they fit into the actual binomial theorem in just a moment. That is yet to be presented. So you're going to iterate your binomial coefficients to be n0, n1, n2, n3, all the way up to n over n minus 1, and then nn is going to be the last binomial coefficient in the expansion using the binomial theorem. So knowing the first two and the last two have these particular values of either 1 or n is going to be very helpful to the process. And these values for particular rows have this structure that's incredibly famous. It's called Pascal triangle. I always called it Pascal's triangle, so I'm very sorry if in my notes I call it Pascal's, possessive triangle. I don't know, that's the way that I was presented with this, so if that's something that sounds familiar to you and you call it that as well, just know that I think that that's perfectly fine because that's the way that I learned it. So Pascal's triangle or Pascal triangle has a very particular pattern to it, which is very easy to formulate, to write down, which is to say that it is ones at the tippity top, the apex of the triangle, it's ones on the outer edge, and then every interior value is the sum of the diagonal 2. So which is to say that 1 plus 1, right, gives us this 2 right here. And then 1 plus 2, right, gives us this 3. This 1 plus this 2 gives us this 3. And so on and so forth. Notice that this 1 and this 3 give us the 4, 3 and 3 make 6, 3 and 1 make 4. And then you can see in these blue triangles how they're trying to, illustrate this, relationship as well. 4 plus 6 gives you this 10. 6 plus 4 gives you this other 10, even though it's not in the blue triangle. The other blue triangle is 4 plus 1 gives you this 5, so on and so forth. And you could surmise the, n equals 6 row of Pascal's triangle. We could write those numbers in as well. I'll write them in orange, in fact, because we're going to deal with an n equals 6 situation in an example that I have coming up, so we could just write it. And we know that there's a 1 on this diagonal to continue. The number in the next step in this n equals 6 row would be 6, because 1 plus 5 equals 6, 5 plus 10 equals 15, 10 plus 10 equals 20, 10 plus 5 equals 15, 5 plus 1 equals 6, and then this last value is a 1. Cool, and you can go on and on and on forever. You can make a Pascal's triangle, infinitely tall, large, theoretically, but, there is a pattern to it, and also you might notice that indeed Pascal's triangle is symmetric over a vertical line going through the apex value. We'll actually talk about that in a little bit more detail, or rather we're going to show this relationship in the very last example of this part of the lecture. Okay, so now herein lies the actual formal definition of the binomial theorem, which is to say that if you have some binomial, which generically they're calling x plus a raised to some nth power, you can use the binomial theorem to expand it, right? Showing every single term individually, and you can also write it using the summation notation that we just recently learned, okay? In which each and every term has a binomial coefficient. The first term has the first element in the binomial raised to the nth power, which might be a little bit more complex than x, and there's no a element in that first term, okay? And remember, we're given what n0 is, as far as the binomial coefficient definition was given to us. It's simply a 1, but we want to show the pattern, so we have this actually formally written when we expand it out, at least in the initial step, and there's no a. Basically the a component in the binomial is raised to the 0th power, so that just makes it a factor of 1. In the next term, we have the binomial coefficient n1, and which what do they describe this symbol n with a something underneath it reads n taken one at a time. So it's like how many times can you take a group of n things one at a time, well, you could only do it n times, right? So that's why n taken one at a time is takes on a value of n. Anyway, we could talk more about that if you'd like, how that's defined and why. But for the purposes of this lecture, I just want to introduce the notation and then learn how to use it as far as the binomial theorem expansion is concerned. Then we'll take a to the a component, so the thing that's being added here, which if it's being subtracted, that sign needs to come in along for the ride, and it's being raised to the first power, although not explicitly shown. And then notice that the x component is raised to the n minus first power, so we're starting to decrease the power associated with the x component by 1, because for every single term, the sum of the exponents has to be n, okay? So the fact that there is no a factor here, it's a is to the 0th power, so 0 plus n equals n, so that holds for the first term. And then the second term, we have a to the first power, x to the n minus 1 power, 1 plus n minus 1 equals n, and so on and so forth. So you can see as later on in the process, you have the exponents summing again to n, and all the way to the last term, in which you'll have a binomial coefficient of n chosen n times, which is just, there's only one way to do that, and then it'll be just the a component raised to the nth power, no x component. Okay, great. So we're going to have plenty of practice where we expand all of that out for some binomials. We're going to have a couple of examples of that. Then the textbooks offers you a couple of other things to consider, okay? And that is this one's going to be particularly helpful for a couple of examples that we will take into account, which is to find, if you just want to find the term containing a particular x component, you could just use this piece right here. So we'll definitely use this formula. And then we have a relationship between the consecutive binomial coefficients and what we can say that they are equal to there. Okay, cool. So let's go ahead and start practicing just by using the binomial coefficient definition with the factorials and all that business here. So we're going to start off slow and easy with a 7 chosen 3 at a time. How many ways can you do that? Okay, so let's give ourselves a good color. We'll go hot pink with it. Why not? That looks cute. So again, we are using the, maybe off to the side here, I'll put the general formula just so we can reference it, which is n factorial over j factorial times n minus j quantity factorial. Sorry, and that is n chosen j at a time. Or n taken j at a time. Whatevs. Okay, those are equal. Okay, so if your n is a 7 and your j is a 3, how do you use this formula in order to find that value? Well, the 7 factorial goes in the numerator, and then j is a 3, so that'll be a 3 factorial right here, and then 7 minus 3 quantity factorial there. Great, so that'll give us 7 factorial over 3 factorial, 4 factorial. Okay, so now is the time where it might behoove us to expand out this 7 factorial. So remember, you can start iterating down that product until you reach one of these factorials, whichever one is bigger. I would say stop at the 4 factorial. So that means that 7 factorial can be rewritten as 7. Sorry, I do not mean to have this little mark right there. That's definitely, there's no negative factors going on here. So this is 7 factorial is literally defined as 7 times 6 times 5 times 4 times 3 times 2 times 1. But go ahead and stop at 4 and put the factorial symbol next to it, which indicates that you would, iterate that product down to the 1. But then we have 3 factorial and 4 factorial. Okay, so notice that you have 4 factorials common that you could just slash away. Boom. Then it might behoove us to actually expand out 3 factorial, and we can see that that matches up with factors up in the numerator. So now we're here with it, and I'm going to expand out 3 factorial to be 3 times 2 times 1. Well, 3 times 2, that is 6, and then the 1 factor we could just kind of ignore. So if you want to, you can slash, slash, slash all of those together, and therefore you will get a final answer of 7 times 5 over a 1, or just call it 35. Okay? There you have it. Okay, now for number 12, this might look a little scary, but do not fret. Remember, there were some, some shortcutty ones that were given to us, so we're definitely going to keep that in mind. For any value n in the top position of this notation, if there's a 0 in the bottom position, it's going to be equal to a 1. So just go ahead and say that is equal to 1 via, n0 equaling 1 for any natural number n. Okay, just as a little bit of explanation there. That was quick, right? So fun. All right, now this one is a little bit more challenging. And I put this one on purpose just because it's, I don't know, it's kind of fun to write all this stuff out. Now I'm actually going to have to give myself a lot of room, and I'm going to change the color just so that it's a lot easier to see and less jarring. So this is basically going to be just using the formula 37 factorial over 19 factorial times 37 minus 19 factorial. Okay, so that'll be 37 factorial over 19 factorial times 18 factorial. Okay, now what do we do with this? Because as you can imagine, 37 times 36 times 35 times 34 and on and on and on and on and on can get like kind of crazy. Now, technically, in order to do this one by hand, you really do have to write down all of those numbers up until, of course, the 19. That's where you get to stop, and you just write 19 factorial. So watch this. This is going to be fun. All right, so I'm going to expand it out, and I'm going to start all the way to the edge of the paper because it's going to get wild as far as like the number of numbers that I'm going to put down. So just bear with me here and just iterate it down. 32, 31, 30, 29, 28. I know, it's crazy. Why am I doing this? This is how it's done by hand. 26, 25, 24, 23, 22, 21, 20, 19 factorial, and leave it there. Okay. So that's the numerator appropriately expanded. I know, wild. And so on the denominator, we could just keep the 19 there. Okay, and you may be tempted to just put what I mean by that is you could keep the 19 factorial there, and you may be tempted to keep the 18 factorial there, but for this process, you're actually going to have to go ahead and expand that one out. So go ahead and say that it's got 18 times 17, 16, 15, 14, 13, oops, that's 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2. I know the last factor of 1 is technically not necessary, but it's, whatever. It's just expanding it all the way out. Cool. Now, I don't know about you, but whenever I have had in an algebraic situation the opportunity to slash a bunch of factors away, I always find it to be very satisfying. And this is an incredibly fun slashing game. All right, let's start with the easy things. Those 19 factorials, those obviously get to go. Boom. And the leftover factors there are 1s, so you could put little 1s there if you want to, or just, assume that there's a 1 left over. Okay, great. Now, we're going to go 18 down to, well, technically 2 and just leave the 1 behind. And we're going to basically slash away their doubles or, whatever appropriate instances of the factors occurring in the numerator versus denominator. But I'm going to start with doubles, with starting with 18. So 18 is a half of 36, so I'll have a factor of 2 left over there. 17's double is 34. 2 left over there. 16's double is 32, leave the 2. 15's double is 30, leave the 2. 14's double is 28, leave a 2. 13's double is 26, leave a 2. You can see where I'm going with this. 12 slashes away with 24, leave a factor of 2. 11 with 22, 2 left over. 10 with 20 and leave a 2. All right, and that's as far as the doubles being taken out. That's the extent of it. Now let's look at this 9 and say, well, where can I factor out a 9? Where does a 9 exist? I'm looking at that 27 right there, and that looks good. So the 9 can go, and the 27 can go, but there's a leftover factor of 3, so make sure you leave that behind. The 8, well, that's the same as 3 of these factors of 2, okay? So I'll slash away an 8, but I have to, with it, oh, actually, I want to do it in a different direction. So I'll slash away an 8, like so, but I got to slash away 1, 2, 3 factors of 2. Okay, you guys following me here? Now the 7 can slash away, so far as I leave it with, take out some other factor of 7. Oh, so the 21 has a factor of 7, but I got to leave a 3, okay? 6 can go if I slash away a 2 and a 3. So 6, but a 2 and a 3. You guys see that? So that 2's gone. 5 can go. Is there any factor of 5 up top? Couple of them. So I'm going to choose to take out a factor of 5 from this 25 and leave a factor up top. The 4 can go as long as I take out 2 factors of 2. 1, 2. There we go. 3, do I have a factor of 3 left behind? I do, so this 3 and that 3, bye-bye. And then one more factor of 2. Doesn't matter which one, just take one more out, and there you have it. So now you have to carefully pick through all of the stuff that's left in the numerator. All of this denominator stuff is technically gone, right? I mean, there's a factor of 1 left. Awesome, cool. We need a factor of 1 down below to make it a whole number. Okay, so now what's left? 37. 35, 33, 31, 29. There's this factor of 2. Sorry, I don't want to overlook that. Oh, actually, you know what? I want to be very careful about this and just scan like very robotically from left to right. So after 31, technically there is a factor of 2 right next to it. Then the 29. Then this 2, and then what do you see? Everything is slashed here. Oh, there's a factor of 5. Then scanning, 23. So the next left factor, and then everything to the right of the 23 is gone, okay? So actually I don't need this last raised dot. So you multiply all of that stuff into your calculator, and you should get, checks notes, 1.76726 times 10 to the 10th power. I know, or some such thing, right? So this is what my calculator gave me as my final answer. If you check this in the back of the book, number 16 that is, they will call it, sorry, let me familiarize myself with what they put. 1 point, what did they go? They went 4 sig figs on this. 7673 times 10 to the 10th. And that's like what they put as the technical final answer. Yeah, when you're plugging this stuff in as your final answer in like a homework or exam situation, they're going to ask you for the specific number of decimal places or whatever, I think, right? Or I don't know, maybe it'll be multiple choice, or you won't be, having to deal with stuff this big. Let's see. Okay, great. So that was fun, right? All right. little bit of a waste of time, I would imagine some people think, and that's okay. I don't disagree with you. Let's go ahead and use the binomial theorem to expand these binomials. Okay, so let's start with a relatively easy one where the x component is an x, the a component is a -1, so it's a little bit more challenging than probably the easiest possible one, and your n value is a 5. Okay, so what does this look like expanded out? Well, we will want to take our first binomial coefficient and have your n value up top, 0 down below, right? And then there's no a value, it's just x to the nth power, which in this case is a 5. So we're going to clean this up to give our final answer, but this is like the first term, right, of our binomial theorem expanded binomial raised to the 5th power. Okay, so that'll be the first term, plus 5, 1. And then we'll take the a component this time, which is -1, to the 1st power. You don't need to put an exponent there, sorry. Get rid of that. And that'll be x to the 4th power, or to the, 5 minus 1 power. Just call it the 4th power, that's fine. Plus 5, 2 for the binomial coefficient. Now it's -1 squared. And we're going to tick down that x to the 3rd power. Now, the exponents of the two components that you have, the a component and the x component, generally that I call it, you have to sum to 5 every time. And if they don't, then that means something's wrong with your exponents. Plus, the binomial coefficient now is 5, 3. It'll be -1 to the 3rd power, x squared, plus 5, 4. Binomial coefficient, -1 to the 4th power, x to the 1st power, just call it x, plus, here's your last term, the binomial coefficient is 5, 5, and it's, there's no longer an x component, it's just -1 to the 5th power. Okay, so how do you get these binomial coefficient numbers? You either use the definition or you look at Pascal's triangle for n equals that number and the values in Pascal's triangle give you these particular coefficients, okay? So however you slice it, you're going to get, for this first one, it's going to be x to the 5th power, because 5 chosen 0 at a time is a factor of 1, so that'll be x to the 5th plus 5 chosen 1 at a time will be 5. Okay, but there's a factor of -1, so we'll, address that in a second step. This one, 5 chosen 2 at a time, gives you a factor of 10. The -1 has 1'd out by being squared. Okay, x to the 3rd plus 5 chosen 3 at a time is also 10. Times now a -1, because it's going to be raised to an odd power, 3 in this case, x squared, plus 5 chosen 4 at a time is 5, and your -1 to the 4th power is just +1, x, and then lastly we have 5 chosen 5 at a time, which will just be a factor of 1 times -1. Oops, not -5. -1 to the 5th power is a -1. Okay, so we can clean this up even further and give us our final answer, in which we have the signage, is going to be alternating. So that'll be x to the 5th power minus 5x to the 4th plus 10x to the 3rd minus 10x squared plus 5x minus 1. And that's your final answer. Okay. Let's do this again, but let's up the ante on the difficulty level here, in which all right, so we need to have the binomial coefficient being 6, 0, because our n now is a 6. So this is where it'll be advantageous for us to look back at our Pascal's triangle that we added an extra row to, because I anticipated that we were going to get some binomial raised to a 6th power. So anyway, let's have the x component, which is x squared. It's a little more complicated than just a simple x. It's going to be raised to the, 6th power. So sorry, it's x squared, but then raised to the 6th power. And there's no a component, which in this case is negative y squared. Okay, so now we'll just add 6. 1 is the next binomial coefficient. I usually do the a component and then the x component, so let's go ahead and be consistent with that according to my notes. That'll give you your negative y squared to the first power, and then your x squared will be raised to the 5th power plus 6, 2, negative y squared to the 2nd power, x squared to the 4th power. And again, your exponents on these two factors here, the a component and the x component, should add up to the n value. If it doesn't, something's going awry as you go, and you want to catch that as early as possible if you do make an error. So the next binomial coefficient here will be 6, 3. Then it'll be negative y squared to the 3rd power, x squared to the 3rd power, plus 6, 4. And I'm definitely going to run out of room, so I'm going to go ahead and continue on another line here, and then I'll clean up house in a subsequent step. 6, 4, negative y to the 4th power, negative y squared, that is. Yeah, x squared to the 2nd power, plus, continue over here. It'll be 6, 5. Negative y squared to the 5th power, x squared just by itself, plus, and here's the last term. You know you're at the last term because the binomial coefficient is the same number in both the positions. Negative y squared to the 6th power, and no x component there. Okay, so then that'll equal notes here are going to give me, okay, so I'm going to go ahead and just write the final answer, and hopefully everybody can follow along with me. I'll try and do this real super slow like. So any natural number, the chosen 0 at a time, is going to be a factor of 1. X to the 2 times 6th power, because the power rule dictates that you multiply the exponents together. That'll give you x to the 12th power for the first term. The second term is going to be negative, right? So we're going to subtract it off. The binomial coefficient is going to be a 6. We know this. And Pascal's triangle, or can, use the formula, what have you. And that'll give you an x to the 10th power, because 2 times 5 gives you 10. Y squared. Then the next term after that is going to be positive or added, because these negative y squared, it's going to cancel out the negative sign. The 6 chosen 2 at a time gives you a 15, right? It'll be x to the 6th power, or sorry, 8th power. 2 times 4 is 8. Sorry, we don't want to add them. We definitely want to multiply them. Sorry for making an error there verbally. And then it'll be y to the 4th. The next term will be negative or subtracted by virtue of the negative y squared being raised to an odd power. 6 chosen 3 at a time will be 20, if I'm not mistaken. Yep. And then the x will be raised to the 6th power, because 3 times 2 is 6. And the y will also be raised to the 6th power. Now we're going to add 15, being the value of 6 chosen 4 at a time. The x will be to the 4th power, and because 2 times 2 is 4, the y will be to the 8th power. Okay. Now, next term after that is going to be negative, because the negative y squared is being raised to the 5th power. 6 chosen 5 at a time is 6, because it's the n chosen n minus 1 at a time. That's always going to be the n value. So that's x squared y to the 10th. And then lastly, it'll be added. 6 chosen 6 at a time will be a factor of 1, and it'll be y to the 12th power, because 2 times 6 gives us 12. Okay. right. So I never recommend that you try and do the binomial theorem straight from what's given to you to the final answer. You really need to write down, in my opinion, now everybody's brain works differently, and if you can capture all of this stuff in your brain effectively and write down the final answer right away, like while doing your work, kudos to you. I can't do it. So that's why I'd at least have to write down this first step using the definition with the binomial coefficient and write down each component with its subsequent decreasing or increasing, depending on which component you're looking at, exponents, and then perform the exponent manipulations after that. That's what I have to do. Okay, but that'll give us our final answer there. Okay, let's go ahead and use some of these, this one formula, really, to get the coefficient of an x cubed term in the expansion of this 2x plus 1 to the 12th power. So we're going to use this formula here. Okay, so let me, write down the formula. So we have an appropriate reference. Actually, let's get this green value or color going on. So the formula that I'm going to reference here is all right, to get the nth term, you're going to use this expression. It's not a formula so much as it is an expression. N, chosen n minus j at a time, times a to the n minus j power, times x to the jth power, where j is the this exponent here. That's your j value. N is the 12th. And that's all you really need. Oh, your a value in this case is a 1. And your x value here is technically this 2x. Okay, so those are all the components that we need. So we're basically just going to feed it into this expression and then go ahead and solve for it. So how will that look? Well, for this particular scenario where we're trying to find the coefficient of the x to the third term in the expansion of 2x plus 1 to the collective 12th power, we're going to go 12, chosen 9 at a time, because 12 minus 3 is 9, times 1 to the 9th power, times 2x to the 3rd power. Okay, so this really needs some work. What is 12 chosen 9 at a time? Well, that'll be 12 factorial over 9 factorial times 3 factorial. Okay, so what I would do here is pretty much the same thing all the time. I would iterate the sum, the product of 12 factorial down to 9 factorial. So it'll be 12 times 11 times 10 times 9 factorial. So that'll allow me to cancel it out with the 9 factorial. And then the 3 factorial, I would actually expand that out, 3 times 2 times 1, because I'm going to try and get rid of all that stuff too. So the 9 factorial is obvi, just cancel. And then 3 times 2 times 1, well, the 3 can cancel out with the 12, but there's a 4 left over, right? And then that 4 can cancel out with the 2, but there's a factor of 2 left over. So what's 2 times 11 times 10 going to yield? 220. Okay. So we're going to use that in order to continue with this process back up here, because I was just via sidebar able to determine that 12 chosen 9 at a time is 220 times 1 to the 9th power is just a 1, but 2x collectively to the 3rd power is 8x to the 3rd. So 220 times 8 is 1,760 x to the 3rd, but we were just asked for the coefficient, right? So the only thing I'm actually going to report for my final answer is the 1,760. Okay, so that was easy enough because the scenario that was outlined fit beautifully with the formula that was given. Now in the next example, number 38, and it's a little bit more tricky, and we have to consider how any binomial that's raised to an nth power, it has n plus 1 terms total, right? Because there's like that 0th term that you need to consider, and so you're going to have to, like, you still use this expression, and we're going to, but we need to do it in a little bit of a trickier way, and I'll show you what I mean by that. Okay, so we're going to find the 6th term in the expansion of, sorry, I am not meaning to find that. So the 6th term is not the same as the term with the exponent of 6 in it, right? Which is what we were using in order to determine right away that j equaled 3 in this previous example. Oh, no. J, in this case, is 5. Now, hear me out, okay? When we're talking about the 6th term, in the sum, the expansion of the binomial, using the binomial theorem, we're talking about, the j being at 1 less than the term number, if that makes sense. So term minus 1 is basically your j value. So let me go ahead and write that down for you. Term number minus 1 equals your j in this formula. So that means, therefore, j equals 5. So we're going to want to keep that in mind. Okay, so if we do that, then we will be able to very cleanly use this formula, which we can reference it real quick. It's this one right here, right? So we can see clearly that n equals 8, no problem there. That's n equals 8. We now see that j equals 5, a equals 2, and the x component is 3x instead of just an x. So using this formula, we will get the following. Okay, so that'll be 8 chosen 5 at a time. The a component, which is a 2, being raised to the jth power, or sorry, the n minus jth power. Okay, yeah, and then the x component will be to the third, the remaining x. Third power. So that's the remaining. Oh, I am so sorry. J doesn't equal 5. N minus j equals 5. J equals 3. Oh gosh, so I totally flubbed this up. LOL. So let me just write, because yeah, j equals 3. My bad. Let me erase this and try and salvage what I've just said here, because it did not match exactly what my notes said. Equals n minus j. N minus j. So therefore n minus j equals 5. J equals 3. I think we're good now. Yes. That all matches up. Oh gosh, I am so sorry for the confusion there. I think we are ready though to calculate this binomial coefficient of 8 chosen 5 at a time. That'll be 8 factorial over 5 factorial times 3 factorial. And of course, I always want to expand this in a very specific way where I'm going to iterate 8 down to 5 factorial. So 8 times 7 times 6 times 5 factorial. I'm going to keep my 5 factorial there, but then iterate the 3 factorial. So that'll be times 3 times 2 times 1. Okay? And then it's slash in time. So 5 factorial is boop, boop, donezo. 3 times 2 is 6. So really we've just got 8 times 7 left. So that'll give me a 56 there. Okay, So I can go ahead and expand this out with what I know about these relatively small numbers raised to powers. And so 8 chosen 5 at a time, I just calculated as 56. 2 to the 5th power is 32. It's supposed to be a raised dot. And 3x collectively raised to the 3rd power is 27x to the 3rd. All right, so what is 56 times 32 times 27? Yikes, a big number. Go ahead and throw that into your calculator and you should get 48,384. And you want that x to the 3rd power as well, because the prompt was originally asking us for the entire 6th term. So you want the whole darn thing, the coefficient and the variable component, if any. And in this case, there was one. Okay, we have one last thing that I wanted to do, which is to show. It doesn't say prove, just to be clear. We're not going to like go back and use the, what do you call it, any kind of method for proving or anything like that. We're just going to show that n chosen j at a time is the same as n chosen n minus j at a time. And this is going to be able to allow us to make this conclusion that Pascal triangle is symmetric with respect to a vertical line drawn from the topmost entry. So basically we're just going to state this just as soon as we are able to show that this is true. So we're going to use the definition of n chosen j at a time in order to make this so. Okay. So first, let's just take this side and say, what does n chosen j at a time look like? That's going to be n factorial over j factorial times n minus j factorial. Yeah? Okay. And then what does this side look like? Well, n chosen n minus j at a time would be equal to n factorial over n minus j factorial times n minus j factorial. Okay, but do a little bit of algebra here, right? And you will get what? Well, putting this here and putting that there, you'll get that the n's cancel out and you're just left with a j. So that means that this is equal to n factorial times n minus j factorial times what? J factorial. Well, wait a second. Isn't that just the same thing here? Aren't these the same? Samesies. Yes, they are, because j factorial times n minus j factorial is the same as n minus j factorial times j factorial. Multiplication is commutative, folks. So we've just shown that these two are the same. So therefore, we can conclude the following. Therefore, Pascal triangle is symmetric with respect, I'm going to just kind of shorthand this, if that's okay with everybody, to a vertical line drawn from the topmost entry. So, yeah. We get to just say that if we're j into the process of Pascal's triangle, or if we're n minus j into the process, we're going to have the same value on either side. So it's like if we start on the outermost edges where it's n0 and then n over n, like we already saw in those general cases, according to the property box that was given in this section, that those are both equal to 1, right? Those are the ones on the outer edge. And then as we go inside the triangle more and more and more for each row, we see that we get those same values when we have j compared to n minus j. Okay, so anyway, that's all there is. As far as material is concerned for this semester, we are that's a wrap. That is a wrap on the curriculum. So let's just spend some time now in class going over these two particular sections, but then also if there's time permitting in the class period, let's start reviewing for the final exam. But do keep in mind that we have another full class period on, I'm going to be real specific to you guys this semester. What date is it? Thursday, December 10th, we're going to have an entire class period dedicated to final exam review. I can't wait to see you in class. See you soon.